This is one of the famous formulas in all of human history. It's the quadratic formula. It describes the zeros of any quadratic function. Most people learn this formula by memory, but very few actually understand why it works, where it comes from, and appreciate the beauty behind its development. Just as a quick recap, the quadratic formula describes the points shown on the graph, which are basically the zeros of any quadratic function. In other words, the points where the function, the line in red, intersects the line x equals 0. In more algebraic terms, the quadratic formula is therefore the solution to the following equation shown on the screen, with the left-hand side being the formula of any quadratic, and the right-hand side being just 0. Interestingly enough, the quadratic formula that we know and love is actually not that old. As early as 2000 BC, we already have records of people working on quadratic problems in ancient Babylon in a far more geometric way than in the way that it is treated today. Then later on in 300 BC, the ancient Greeks were already dealing with special cases of the quadratic formula with explicit solutions. This continued in 600 to 980 with Persian and Indian mathematicians dealing with more special cases of the quadratic formula with explicit solutions again. But it really wasn't until 1637 AD when we got the quadratic equation that we know and love today with all of its beautiful notation, when we got all the solutions to any case of the quadratic formula, not just the special cases. So we can see that such an elementary formula as the quadratic formula is not even 400 years old yet, which is quite amazing in my opinion. But enough about its history. Let's actually try and solve the quadratic formula now and derive where it comes from. So we start with the equation here on the screen, and one thing we can do is just try and solve for x to get the quadratic formula. To do this, one place where it can start is just by noticing that if a is not 0, we can divide everything by a. Now we want to isolate x, but we have terms here with x squared and x. So one trick we can use is just to complete the square. I'm not going to explain in detail what this entails, but just notice that the following formula here will give a nice identity to work with. The formula on the bottom is very similar to the formula on top, but on the left-hand side of the formula on the bottom, we have x contained in these parentheses, which is very useful if we want to isolate x. In fact, if we just rearrange the formula on the bottom a little bit, we can make it look a lot like the formula on top. And now that we have them so similar, we can actually just substitute the bottom one into the top one to get a very nice expression for x. Now we basically have x containing these parentheses, and all that remains is just to algebraically manipulate this and simplify to get x on the one side, which shouldn't be so difficult. First, we move terms on the other side. Now, we can simplify this fraction a little bit and make a common denominator. Already here, we can also tell we're getting close, because we have b squared minus 4ac already on the numerator of the right-hand side of the equation. So we know we're doing something right. Now, let's go further. We can take the square root of both sides to get it even more simple. Finally, we just subtract minus b over 2a, and we get x on one side. Simplifying a bit further to get a common denominator, we finally get our beautiful quadratic formula as we know and love it. But what we really fail to appreciate as well is how beautiful and how useful this quadratic formula is. Because notice that if we just rewrite this formula in terms of its form as shown before, we have now that this basically tells us there's a sort of symmetry to the solutions to the roots of the quadratic, and that they are both symmetrical across the line of symmetry. So if you take the point minus b over 2a you either add the square root of b squared minus 4ac over 4a squared, or you subtract it. But whichever one of those choices you make, you will always end up at a root. So this tells us that if we just, ignore the plus or minus term, we have that negative b over 2a as sort of a line of symmetry for the quadratic. And of course, the distance from the line of symmetry to each root is just the square root b squared minus 4ac, all over 4a squared. But what we really fail to appreciate as well is how beautiful and how useful this quadratic formula is. Because notice that if we just rewrite this formula in terms of its form as shown before, we have now that this basically tells us there's a sort of symmetry to the solutions to the roots of the quadratic, and that they are both symmetrical across the line of symmetry. So if you take the point minus b over 2a, you either add the square root of b squared minus 4ac over 4a squared, or you subtract it. But whichever one of those choices you make, you will always end up at a root. So this tells us that if we just ignore the plus or minus term, we have that negative b over 2a is sort of a line of symmetry for the quadratic. And of course, the distance from the line of symmetry to each root is just the square root b squared minus 4ac, all over 4a squared. I hope that's a cool way of understanding the quadratic formula, where it comes from and what it actually means in a term. In a way, simple. I know that a lot of people don't actually learn why this works in school, and I thought it was super cool when I first learned why it works. A really interesting further question you might have is, well, what if we didn't have a quadratic equation with powers of 2? But what if we actually had an equation that included powers of 3, such as the cubic equation shown right here? Can we still solve this to get x on one side, and then all the other constants on the other? The answer in this case is yes. We can have a cubic equation, which we have x is equal to very long equation, where's a lot of constants, which I'm not going to write out right now. But interestingly enough, we can solve this equation, and now you might ask, well, what if we have powers of 4, so x to the 4th? Well, can we still solve this equation? And the answer, surprisingly again, is yes. We can still solve this in terms of x. But if we take powers of 5, can we still solve that? The answer, interestingly enough, is no. In fact, in any general case, for something with powers of 5 and above, if the constants are all, non-zero, and this is not a special case, we in general can't solve this equation in terms of x. So there's no way to rearrange it and do any sort of algebra to get x on one side and everything else on the other. Which is quite interesting because why should it be at 5 that this pattern stops when it worked for 4, 3, and 2? The answer lies in a very beautiful and very deep area of math called abstract algebra. And today we're not going to cover this in this video, but that's just an introduction to some of the main questions that motivated abstract algebra and some of the beauty behind it. I hope you enjoyed this, and thank you so much for watching. If you ever need help with your homework, feel free to send it to my email, and don't forget to subscribe to my YouTube channel for more math tips. See you in the next video.